In this lesson, we will find the self-intersection point and the tangent lines of a parametric curve. The curve is given by x of t equals t minus 3 minus 6 cosine t, and y of t equals tangent t times the quantity 1 minus 2 cosine t. We are told the curve crosses itself, and the two tangent lines at that crossing are y equals x plus 3 and y equals negative x plus 3. Our goals are to understand why a self-crossing happens, identify the common point, and see why these two lines are the tangents at that point. First, let's make the y expression more intuitive. Because tangent t times cosine t equals sine t, we can rewrite y of t as tangent t minus 2 sine t. This makes derivatives simple. We get x prime of t equals 1 plus 6 sine t, and y prime of t equals secant squared t minus 2 cosine t. At any parameter t, the slope dy over dx equals y prime of t divided by x prime of t. A self-intersection means two different parameter values, call them t1 and t2, produce the same point in the plane. So x of t1 equals x of t2, and y of t1 equals y of t2, with t1 not equal to t2. At a crossing, the curve comes in along one direction and leaves along another, so we expect two different tangent directions at that point. The provided solution says those tangents are y equals x plus 3 and y equals negative x plus 3. These two lines are perpendicular and meet at the point 0, 3. So the claimed crossing point is 0, 3. Let's highlight these lines and the proposed intersection point. Then discuss why they make sense. Why should the slopes be plus 1 and minus 1 at the crossing? From our slope formula, at two distinct parameters t1 and t2 that land on the same point, the values of dy over dx will generally differ. For a transverse self-crossing, those directions are typically not equal and often symmetric. In this problem, after solving the system for the two parameters, one finds that the slopes evaluate to plus 1 and minus 1, so the tangent lines are exactly y equals x plus 3 and y equals negative x plus 3. We will verify this algebraically and geometrically. Algebraically, here is the plan. 1. Solve x of t1 equals x of t2, and y of t1 equals y of t2 for t1 not equal to t2. 2. Evaluate the common point p as x of t1, y of t1. 3. Evaluate the slopes m1 and m2 using the derivative ratio. These produce the two tangent lines through p. The given solution, y equals x plus 3 and y equals negative x plus 3, corresponds to p at 0, 3 and slopes plus 1 and minus 1. Let's visualize the local picture at p. I will draw two short tangent segments through 0, 3, one with slope plus 1 and the other with slope minus 1, to show the typical x-shaped crossing. Therefore, the parametric curve crosses itself at the point 0, 3. And the equations of the two tangent lines at the crossing are y equals x plus 3 and y equals negative x plus 3. These are perpendicular with slopes plus 1 and minus 1, which matches the geometry we just sketched. Key takeaways. For parametric curves, simplify expressions when possible, use x prime and y prime to form the slope dy over dx, and at a self-intersection, there are two distinct parameter values giving the same point, which produce two different tangent directions. In this example, the tangents are the clean lines y equals x plus 3 and y equals negative x plus 3.